talking real-world smart contracts on Corda. And the reason why I like to share that is when I joined ING's blockchain team in 2016, we were doing a lot of tests, pilots, proof of concept. Basically, the whole world was doing tests on blockchain. But obviously, the goal of doing those tests is bringing them to production to actually grasp the benefits of it. And in that journey, to bring these blockchain applications from a test to really production-worthy applications that are safe and reliable to operate, we learned a lot. We faced a lot of technical challenges, and we learned a lot while solving them, and I want to share those learnings with you. But before we get there, I'd like to see who we have in the room. Who of you has programmed smart contracts? Whether it's Solidity on Ethereum, or chain code on Fabric, or JVM code on Corda? Some hands. I see some hands. Not not very many. That's fine. All right. So in 2008, the Bitcoin white paper was published. And besides the cryptocurrency, which is very famous, this was the first introduction of blockchain technology to the world. So Bitcoin can be peer-to-peer, completely decentralized, because of the underpinning blockchain technology. This year, 2019, we see blockchain applications going into production, real mainstream applications. For instance, Congo, trade finance, commodity trade finance application. It runs on Quorum blockchain. And HQLAX, a collateral lending solution. Basically, it's for banks to trade securities with one another in order to meet the capital requirements, specifically the liquidity coverage ratio, or LCR. And ING has been closely involved in these two startups. The initial code base of HQLAX, the initial versions were developed by us. Congo also started as an idea within ING, and then other banks joined as well, because we all saw that trade finance could become much more efficient on the blockchain. And both Congo and HQLAX, the CTOs of those startups, they are ex-ING blockchain team members. So that's from 2008 to 2019, and actually, yeah, 2009, 2010, people started to understand that blockchain technology was not restricted to cryptocurrencies, and it could be used in many other applications that would benefit from this decentralization. So that's 11 years. What took us so long? So to do a proof of concept with blockchain, that's one thing. But to run one in production, that's really something else. You'll face some technical challenges. For instance, contract upgrades. Smart contracts, or the business rules in which, with which you can allow updates of the ledger, they're immutable by nature. And that's one of the characteristics of blockchain. Privacy. Unlike traditional centralized systems, where one party gets to control who can access which data, decentralized systems like blockchain or DLT, they rely on the fact that multiple parties can verify and validate transactions. In order to do so, transaction data must be shared with these multiple parties, and confidential information can leak to those validating organizations. Very concrete. If you look, for instance, at Bitcoin, everybody running a full node has a full copy of every transaction that ever happened. So you can see every Bitcoin transaction. You can see from which Bitcoin address to which Bitcoin address payments were done. In Bitcoin, in the case of Bitcoin, it's hard but not impossible to reveal the real-world identity behind a Bitcoin address. In the blockchain applications that we use, the so-called permissioned networks, we run blockchain networks with known participants. So you know which address represents which network participant. Integration with IT infra. There are some specifics, we'll get to that. And also performance. If you run your data in traditional centralized application in one data center, that's definitely something else than when you have a globally deployed network with nodes that need to reach consensus on validity of transactions. That really typically slows it down. But we have some solutions for that, and we'll have a look at that. So the good thing is, these challenges, they can be solved. And our tool of choice is Corda. It's a JVM-based distributed ledger technology. We like to nickname it the blockchain that's not a blockchain. If you look at the definition of a blockchain, the definition says that it should group transactions in blocks which are chronologically linked to form a chain. I'd say the fact that these transactions are grouped in blocks, that's an implementation detail. I'd say the significance of blockchain comes from its unique benefits. To have an immutable, trusted, shared ledger of data, where you can trust that as long as the majority of the participants are honest, only valid transactions will be recorded on that ledger. So the fact that Corda does not group the transactions in blocks, transactions are linked but not grouped in blocks, that officially does not make it a blockchain, but I don't really care about that because it has the same benefits as a blockchain. So the official term is Distributed Ledger Technology, DLT. Here you see 4 different organizations, A, B, C, and D, all running a Corda node. And you see something we call trust boundaries. These organizations do not necessarily need to trust each other. Now, one Corda network can run over these different trust boundaries, and still we can trust that the ledger will only contain valid transactions. If you look at how we do business today, ING is a large bank, and we do, for instance, a lot of payments with other banks. We don't use a DLT for that. So basically what we do is, at the end of the day, we exchange an end-of-day statement to see if what we think is our truth, the number of transactions that we send back and forth, it actually is it the same as the other bank. We exchange end-of-bank statements to do that in a process called reconciliation. And guess what? They don't always add up. We need to make phone calls to fix that out, to iron it out, etc. With Corda, you know that the data that I see is consistent with the data that my counterparty sees because of the built-in consensus algorithms, deterministic smart contracts, and the cryptographic functions. It says here trust boundaries. Typically that's different companies, different organizations. You could also think of if you have a large multinational doing reconciliation between the head office and a local branch somewhere else in the world, then you could also have a trust boundary within one company. This is also where a DLT, like Corda or a blockchain, is different from a distributed database, like Cassandra or Oracle DataGuard. Those are designed to run within one trust boundary. They can run in multiple data centers on multiple nodes as long as they're controlled by one organization. And in Corda, it's distributed. It can be run over multiple organizations and still be consistent and trusted. Unlike Bitcoin and Ethereum, where all the transactions are shared with all the participants, in Corda, transactions are shared on a need-to-know basis. So if there's a transaction going on between Ed, Carl, and me, like transaction 3, only they will find out about it. Corda uses UTXO, or unspent transaction output, which means that every transaction consumes states, input states, and produces output states. States can be consumed only once. Corda verifies the transaction history. So every recipient of a state, in this case Bob, who gets to become the owner of a cash state, he can verify the history of that state. He can verify that in the previous transaction, Alice became owner of this cash state, which was signed by Dan, and he can also verify how this cash state got issued in the first place, in the first transaction, by Charlie to Dan, and how it was digitally signed by Charlie. So everybody who receives a state can verify the provenance or the history of that state. Corda uses a notary service, a consensus service. It provides consensus on uniqueness, ordering, timestamping. Uniqueness, in order to prevent double spend of that state. If you have a state that represents, I don't know, €100, you can spend it only once, and then you're no longer the owner. Ordering and timestamping, things that are not trivial in a distributed system with latency of the messages going back and forth. And optionally, transaction validity is verified by the consensus service. Ideally, you would want that to avoid invalid transactions to be recorded on the ledger. Then it will become tamper resistant. You could also choose to use a non-validating notary service to make it no longer tamper resistant, but it is still tamper evident. If somebody would try to record a transaction which is invalid, it would be immediately evident to everybody. And you could argue that in a permissioned network with known participants, that would work. Well, ideally, you want the validating notary service. Notary service has pluggable consensus. In theory, you could plug in proof of work, like in Bitcoin and Ethereum. In practice, we see a Raft and BFT Smart being used. It's always high available, so the service is always composed of several nodes. If one of them goes down, still the service remains available. Crash failure tolerant, as we call it. And optionally, depending on which consensus algorithm you plug in, it can also be Byzantine fault tolerant. So it can be operated by multiple organizations. And if a minority of those organizations, less than 33%, tries to record invalid transactions, then still they would be rejected by the honest majority. So you can choose which consensus you want. All right, like I said, contract upgrades. By definition, smart contracts are immutable. However, obviously, if you have a production system, you might want to add a new feature. You might want to apply a bug fix, or there's new compliance rules which require new features to be added. So you must be able to change that. If you even zoom out and you look at the Accelerate book, it did extensive research on what makes IT organizations effective and how to even measure that. When I started working in the late 90s, my manager used to measure how many lines of code I was writing as an indicator of productivity. Well, fortunately, those times have gone. These metrics are more representative of the success. So things like deployment frequency, lead time, mean time to restore, and change fail percentage. You see that the top 3 is also related to how fast can you change your software, in this case, smart contracts. In Corda, there are two types of upgrades. Implicit, where you pre-authorize future changes, and explicit, where you need to agree with every change. Implicit can be signature constraints. You say that, you know what, every contract implementation that comes from a jar that's digitally signed can be used. And this signature can be set by one organization, or it can be a threshold signature. So if you have a blockchain network of, I don't know, 11 participants, and you say as long as 7 out of 11 agree, then we should go through with it. Network constraints, so basically on the Corda network, one network operator says which jar files can be used, and it records per class name of a contract also the hash of the jar file that's providing it. A single hash constraint, only one jar file can be used, one implementation, or explicit. It requires a special contract upgrade transaction, and it requires all of the participants to sign that state to be used in a contract upgrade flow. So basically it's a trade-off. Do you want implicit, which gives you an easy upgrade process, but it requires faith in third parties? Or do you want explicit, which has a heavyweight upgrade process, but it provides full control of change acceptance? Which one's bad or right? I leave it up to you. We use both. But I'm going to demo the last one, the explicit one. We're going to look at some Kotlin code. Corda runs on the JVM, so you can program any JVM language you like. Corda itself is built in Kotlin, but obviously you can interface with it in any language you like, any JVM language you like. We chose Kotlin. It's the favorite in our team. I have a very easy, simple contract here. It only allows creation of states, in this case an IOU state. It only checks one thing, that the issuer has signed it. And what I'm going to do next, I'm actually going to call my application, and I'm going to create a transaction that issues this particular state. You see it's connecting to party A. I have a network running on this laptop with 3 Corda nodes. They're quite lightweight processes. Party A, party B, and one single notary. Obviously, normally a notary is a cluster of multiple nodes, but for testing purposes on this laptop, I have only one. And I just created one state. It's in the vault of party A and B. In this case, it's showing the one in party A. And you see to which class, which contract class it's linked, and also the hash of the jar file that can provide it. So what I'm going to do next is I'm going to change my code. I have a nice script for that, actually. And let's see. I'm going to show that to you. Here you go. And you see I added some functionality. So besides the create, there's now also a transfer. So there's more logic to it. And you see that my contract, the IOU contract, it now extends upgraded contract with legacy constraint. It contains the hash of the jar file that should be used in the upgrade, and it overrides the upgrade function. I also added a field. It will now contain currency, and because my previous transaction did not have the currency field, I will fill it with a default value, in this case euro. So I changed my code. That means I need to rebuild my application. And after that, I will distribute my jars to all the nodes, 3 in this case. And normally, now it's a local file copy, but obviously normally you would have some secure way to distribute them to all the network participants. Last but not least, I'm going to restart. I'm going to restart all 3 nodes, which gives us time to look at the client that I'm using. See, initially we called the create, which created these states. And it also supports an authorize and an execute. Now, I created a state on the ledger in which 2 parties are involved, party A, party B. So the only way to upgrade it is if one of those, doesn't matter who, one of them needs to authorize and then the other can execute. So if you have a state with 10 participants, 9 of them need to authorize and the last remaining one can then execute, which makes it very explicit, this authorization that you need for it. Let's see where we are. Okay. All right. So next is what I'm going to try to do. I'm going to try to execute the upgrade without it being authorized, and that should result in a failure. In this case, party A tries to authorize it, but the counterflow, so party B, he rejected, so their counterflow errored. So what I need to do instead is first authorize and then execute. Yeah, it's still the V1. And now I'm going to execute. And now it works. And now we see the state in the vault. It's referring to V2. And it also has besides the amount, it also has the currency field, the euro. So you see this funny thing that I use versions in the package name. And normally you have different versions in Git or any version management system, but it's not reflected in the name of your implementation. But because I have a transaction that consumes states with the old implementation and produces them with the new implementation, I need both versions to be in the same JVM process, in the same class loader at the same time, which is only possible technically if they have different names, which is why the version name is in the package. All right. So that was the demo about the contract upgrade. So just remember, there's 2 ways to upgrade in Corda, implicit or explicit, where explicit is a more heavyweight process, but it gives you more guarantees of what you accept. You can build similar things in Ethereum, where you have you can have a proxy contract that forwards you to a specific version of the business implementation, and that version can change. The address of the actual business logic contract can change over time by the network operator. All right. So how about privacy? I just briefly explained how Corda works, and it really helps that it does not globally share all transactions, but only on a need-to-know basis, selective multicast as they call it. However, still there are 2 ways in which it can leak confidential information. For the transaction history verification, if you remember the slide with the 3 transactions, you can verify and trace back the whole history of that state by going back over the transaction history. And also the validating notary. It will need transaction information in order to run verification. And particularly if you have a notary which is operated by multiple organizations, then they all get to know about your transactions, which is undesirable. So there are ways to allow verification without sharing all the details. One of them is through secure computing, for instance, Intel SGX, and the other one is through cryptography, for instance, zero-knowledge proofs. So how secure computing works, if you look at SGX, it has a built-in private key, which is unknown to to anyone. It's unknown to the owner or the operator or the root of that machine. And it has an isolated part of memory called Trusted Execution Environment, or enclave. This enclave cannot be accessed by any other process. Not by the operating system, not by the BIOS, not by any other privileged code. How that works in blockchain is that you can share transactions as long as they're encrypted, and then they can be decrypted by the private key, which is built in the processor. It runs the decryption and the validation of the transactions in the enclave, which cannot be accessed by any other process. So basically, your machine, your SGX machine, it runs the verification, and still the owner or the ops engineer of that machine cannot access that data. In that way, you could have decentralized verification, transaction verification, which is required for the blockchain consensus, without leaking any information. It's conceptually strong. You see that a lot of big names are investing in this technology. There are also some concerns. For instance, you need special hardware, and many large organizations have standardized hardware. Obviously, it's a vendor lock-in. Key management is more difficult if your key is hardwired in your CPU. We saw many different attacks on enclaves where they're supposed to be isolated, but still data could be extracted from it, for instance, through side channels. For instance, Spectre and Meltdown were famous or infamous. And as soon as they were published, within a couple of days, also source code appeared on GitHub on how you could exploit SGX enclaves using Spectre and Meltdown. And it also requires some developer awareness. For instance, the enclave is very small, and ideally you'd have a stateless application running in the enclave, which allows for replay attacks. So conceptually strong, but not very mature yet. Another way to solve the verification without leaking information is cryptography. For instance, zero-knowledge proofs. By definition, a zero-knowledge proof allows a prover to cryptographically prove that a statement is true, and a verifier can verify that, but no other information but that statement, other than that statement, is shared. The real-world analogy of a cryptographic zero-knowledge proof would be Alice in a cave. This cave has a door that can only be opened if you know a secret code. If Bob sees that Alice goes in entrance A and exits in B, or vice versa, he knows she must have opened that door. She must know that secret code. So Alice can prove she knows that code, but the code is not revealed. That's the real-world analogy. Examples of zero-knowledge proofs in blockchain, for instance, Zcash. It's a publicly tradable cryptocurrency. It uses Zcash snarks, generic zero-knowledge proofs. Monero, it uses range proofs to prove that all the in and outputs of transactions are positive, along with ring signatures and homomorphic encryption. Mimblewimble, it's a privacy protocol on top of Bitcoin. And Hyperledger Fabric, it uses zero-knowledge proofs for zero-knowledge asset transfer and identity mixer. You see that Zcash, it's a public blockchain, a public cryptocurrency. So anybody with internet can download a Zcash client and try to hack it. So it runs in production since 2016. So it's basically, fair to say it's battle tested. I think many people would want to hack it and assign some of the built-in cryptocurrency to themselves. So we feel in ING that a zero-knowledge proof is a very powerful privacy solution, which is why we invest also much in it. You see, for instance, our work on Corda, where we the privacy fix we have for R3's Corda blockchain. It's basically integrating the validating notary that you ideally want with a zk-snark library from libsnark. We also built bulletproofs. It's a more efficient zero-knowledge proof protocol. We wrote that in Go to integrate it with Ethereum. And you see the work we did on a range proof. Basically, a range proof allows you to provide proof that a secret number lies in a known range. For instance, if you need to prove that you're an adult, then you can create a cryptographic proof that your age is between 18 and some arbitrary high number like 300. And anybody can verify that proof, but your age will remain secret. Yeah, we got a lot of feedback from the community, including Ethereum founder Vitalik, who responded to that. Right, so how about integration? If you look at blockchains like Bitcoin and Ethereum, they have full replication. So every node contains all the transactions that ever happened on that blockchain. That means that redundancy comes out of the box. You can run as many nodes as you want. If you look at how these nodes communicate, every Ethereum or Bitcoin node, it connects to 10 or 20 other nodes, and transactions are propagated from those connections to 10 or 20 others, etc., until they reach the whole network. That's not how Corda works. Corda uses peer-to-peer messages, like we saw in the introduction, only transactions are shared on a need-to-know basis. This also means that redundancy does not come out of the box because messages are sent to a specific address. So we need a redundant setup. And also, because of these peer-to-peer messages, if we have a Corda node behind a firewall, then for every node on the network which is added or leaves the network, we would have to do changes to our firewall configuration. Well, on a large network, that would be unfeasible. The other option of not using firewalls and just connecting the Corda node to the directly to the internet, it's also undesirable because it contains a lot of business logic, a lot of data, which is why we have specific components. The DMZ float listener, so basically proxy components that we can run in our DMZ that proxy the Corda traffic. So how about performance? Like I said, if you have a distributed application, an application that can run potentially over the world, and if you have a consensus algorithm that needs to be Byzantine fault tolerant, it basically requires a lot of messages to go back and forth between those nodes, that will have an impact on your performance. Though there are no standard ways to measure, it's safe to say that a Corda RAS-based notary service can reach up to 100 to 200 TPS. So other blockchains like Fabric or Quorum, they might come up with very high numbers, but then, because there's no standard way to measure this, it's hard to compare what it actually means. But it's good to note that though this notary service is required to reach consensus, the network capacity is not limited to the notary capacity, because you can have multiple notaries on one Corda network, as long as you have one notary per state. So let me give you an example. If you have an application that processes international payments, so payments in euros and in USD, etc., then you need one notary service per currency. You need to make sure that every euro is spent only once, or every euro token on the ledger. Same for USD. So you'd have a USD notary cluster and a euro notary cluster. And only when you do FX, When you go, when you pay from euro to USD and vice versa, then you need to migrate the states from one notary to the other. So then you do have a performance impact. But long story short, the total performance of the network is not limited by the capacity of the notary service. So 100 to 200 TPS, that's quite a large range. It depends also on the size of the transactions. If a transaction has a lot of input states and a lot of signatures to verify, obviously the more signatures to verify, the longer it takes to validate a transaction. So to be on the safe side, you see the initial go-lives that you see this year. They are with core apps that have a lower volume, so typically a couple of hundred or 1,000 transactions per day, not per second. So to summarize this story, we faced engineering challenges while bringing blockchain applications to production with regards to contract upgrades, privacy, integration with existing infra, and performance. But the good news is these challenges, they can be solved, and you can run blockchain applications in production today. That's it. Are there any questions?
Thank you, Cees.
Thank you.
And we do have, we've got plenty of time for questions, okay? And I know we have a lot of questions.
Yeah.
From your talk. Yuri especially is very curious to know, what do you think is the biggest bump in the road of commercial usage of blockchain technologies?
Well, one thing that was a bump for us that required a lot of attention was the identification of what is a good fit for blockchain. The initial thought we had was basically payments and FX payments, so cross-currency payments. If you do a payment from one small currency to another small currency, like Polish zloty to Mexican pesos, it could take several days for your payment to end up. And this payment can go through several banks, and it can be lost in between. So that sounded like a good fit. But then again, if you look at how payments work and why it's designed to work like this, the correspondent banking model, then basically payment systems are always a compromise between cost, risk, and speed. And you cannot solve all three of them just by different technologies. So though we are still looking in that area, it was basically not the best fit to start with. You saw that the first application that went live was a trade finance application, and there we do see a great fit. Because if you look at the world of trade finance today, actually paper documents with wet signatures, so handwritten signatures on it, they are physically sent all over the world to prove that a buyer has a bank guarantee that the payment will arrive, or to prove that the customs documentation is in order, that the goods are insured, etc., etc. So there we can really leapfrog and use a blockchain and the trust provided by blockchain to automate that. So unlike previous attempts in the past decades to automate trade finance administration, all these attempts were in centralized databases. And then if you're in some far corner of the world and there's a customs guy looking at a screen from some Amsterdam-based startup that says, yeah, you know what, there's the goods will be paid and there's an insurance, then why should he trust that? Whereas if it's a blockchain system, the same trust we have when we do Bitcoin payments or when we use Ethereum, we can use that trust also to make the information for trade finance trustworthy and trustable all over the world. So yes, long story short, what was the biggest bump? It was the identification of which use case to use.
Okay, thank you. And another popular question here. Do you have any thoughts on the topic of blockchain and gaming?
Well, I'm quite a fan of gaming, but when it comes to blockchain, and if you remember the last topic, which was related to performance, I see the high performance needs of gaming not such a good match on the current state of technology of blockchain today. So basically, the first use cases we're looking at are low volume applications to run on blockchain. That said, maybe on a side note, the SGX technologies, the secure computing, this principle that your machine, your computer knows more than you do, it actually comes from gaming. So there's the first-person shooter games where your PC already knows there's an adversary hiding around the corner where you don't know it, because it would be competitive advantage, and your machine would not doesn't need to retrieve that information over the wire as you go around that corner. It needs to already have that information, but it cannot share it with you. So that's a similar concept. But in general, so the combination of blockchain and gaming, I don't see that fly very soon on a big scale.
All right. Okay, next question. If the information is not distributed over all nodes, what happens when nodes with unique information are down?
Well, if a node goes down and it recovers, the information is not lost. So I think the problem you need to address, if the information is not shared globally, but a node has unique information, the problem you need to address is what happens when I send an update to that node while it's down. Do I know if it's if it will process it, or do I know if it's down or just slow? In a distributed network, you need to make certain assumptions there. In Corda, this is solved by using AMQP for reliable message delivery. So only when so messages are queued, and only when an acknowledgement is received from the recipient, only then you know for sure that it has received it. Unlike Ethereum and Bitcoin, where you can just be down and restart in a week and it will synchronize with the rest of the network, that is not possible. So basically, all the messages sent specifically to you, the sender will know you weren't available, so there will be no inconsistencies. And every operator of every node itself is responsible for making backups in order to restore that node.
Okay, good. I think we've got time. We'll take one more, and this one is how to start with blockchain in general. Your advice for beginners?
Well, as much as I'm a fan of Corda, I think Ethereum is the easiest to start with. And good thing is also they have a testnet, a global testnet, to which you can connect. Also public net, obviously. So you don't need to run any infrastructure yourself. It's already available. If you Google how to get started with Ethereum, I think one of the first hits you'll find is to build an Ethereum app in 2 hours or something like that. That's where I would start if you want to get your hands dirty. I think that's a good way to get started. There's the Ethereum white paper, which then gives you more background. Same for Corda. There's a lot of documentation and tutorials to get started there. Obviously, Corda is a good match to enterprises based on the enterprise standards which are used, so JVM, AMQP, and the X509 certificates. And obviously, there's a lot of documentation on Corda.net to get started, but I think the easiest way to get started with blockchain in general is with Ethereum. One last advice there. There's a really great white paper from Princeton about Bitcoin. If you read that, you know a lot of the background about the cryptography used, about the consensus algorithms, and it's really a good start. If you want to get started with blockchain, start getting your hands dirty, but also read some background. The Princeton paper on Bitcoin, it's available as a white paper, as a book, as videos on YouTube, so it's, but the content is really good.
Okay, very good. Round of applause for Cees. Thank you again.
Thank you.